Welcome, everyone. Thank you for joining us in the first webinar of our PID Workshop Series. Um, my name is Aaron Ostland. I am a Research and Extension Specialist with North Dakota State University, and I am representing the Soil Reclamation Laboratory on behalf of myself and Dr. Miranda Meehan and Dr. Thomas DeSutter. Today we are going to be mostly focused on photoionization detection, and we have a guest speaker, Justin Blackman, who's going to share some insight into advancements in the technology and specific applications that might be pertinent to some of you practitioners in the field of remediation and reclamation. Before I hand it over to him, I'm going to go through just a little bit of background of what the Soil Reclamation Laboratory here at North Dakota State University is up to and how we have gotten to the point of jumping into a webinar and workshop series around photoionization detection. So the Soil Reclamation Laboratory at NDSU is dedicated to both research and extension projects in soil reclamation and remediation, particularly in response to energy development here in North Dakota. So our mission aligns with North Dakota's coat of arms, which proudly states strength from the soil, demonstrating our commitment to safeguarding one of our most precious resources. As a land grant institute, North Dakota State University is committed to environmental stewardship, and the Soil Reclamation Laboratory plays a critical role in achieving this commitment by identifying soil degradation risk and developing solutions for mitigation. Our multifaceted initiative focuses on advancing research on soil remediation and contaminant management, developing practical management tools for stakeholders, and fostering collaboration across industry, government, and academia to tackle the most pressing challenges in soil and environmental restoration. So today's first in the PID workshop series is part of a larger effort to identify environmental risks from energy development, such as hydrocarbon spills, and have a lasting effect on soil health and ecosystem function when those types of events happen. And so, mitigating these risks is essential to maintaining productivity across our landscape, both for ecological function and agricultural practices. So photoionization detectors play a key role in detecting volatile organic compounds. And at impact sites, they allow us to do proper delineation so that we can identify where environmental risks exist and be thoughtful about the resources that we allocate to those areas. So the PID workshop series is designed to bridge the knowledge gap between equipping field staff with technical understanding, between needing to maximize the potential of this photoionization detection and how that leverages our ability to do effective environmental assessment and remediation. So this is just part of a series, and we hope to continue to build on this and ultimately equip our stakeholders with more skills and knowledge around how we can effectively integrate this technology into remediation and reclamation. Just a couple touch points on our efforts in the research and extension programming at the Soil Reclamation Laboratory. We integrate our research programs, our extension programs with our stakeholders through the utilization of a reclamation advisory group. And so over the past year and a half or so, we've focused on fostering collaborations between key stakeholders in reclamation and remediation, working to have a good back and forth working between the folks within our laboratory and our extension program and the practitioners and folks that are actually out there on the landscape integrating remediation practices within energy development in North Dakota. And so our aim is to facilitate ongoing dialogue that guides both our research and educational outreaches, but also the practical practices of reclamation in North Dakota. Just a little bit more context, North Dakota's leading industries are agricultural and energy development. And so understanding that those two have a lot of overlap and contribute significantly to our economy demonstrates the impact that things like soil health can have on both energy development and the longevity of our agricultural economy. We are still seeing quite a bit of development associated with energy development. And so I tend to stick with the numbers of about 500 miles of new pipeline construction every single year, resulting in roughly 6,000 acres of additionally disturbed lands through the development of energy infrastructure. And then we're still looking at about an average of 3 spills per day when we're monitoring both hydrocarbon and produced water releases associated with energy development. And so it's critical that we understand the need for identifying these spills and properly delineating them, and so that we can return those soils to their pre-disturbed productivity levels and maintain that commitment to our soil resources here in North Dakota. And with that, I'm going to give us a quick outline of what we're talking about here today with the PID Workshop Series on advancements and applications in PID technology. And so we're going to do a kind of an introduction on what photoionization detection is and where that technology is useful in the remediation and reclamation of contaminated soils. And then through there have an opportunity to kind of set the stage for what we hope to have future opportunities for not only additional webinars, but hands-on opportunities to further develop skills for practitioners that utilize PIDs in the field. And so with that, I'd like to introduce our guest speaker today. Justin Blackman is joining us today from Ion Science, which is a leader in PID technology. He has served in multiple roles over his 25-year career with Ion Science. His technical expertise spans from electrical engineering and high-level instrument calibration for oil and gas applications. Over his career, Justin has worked closely with clients to optimize their use of PID instruments, ensuring that they get the most accurate and reliable readings in challenging field conditions. And with that, I'm going to pass it over to Justin. Thank you.
Thank you very much. So, good morning, good afternoon, wherever you are, folks. I'm actually afternoon at the moment talking from the United Kingdom, but the beauty of these webinars, we can be wherever we want in the world. I see online we have a really nice mix of people, previous knowledges. So I'm going to go kind of right down the middle. Assuming some people know a little bit, and hopefully everyone can come away knowing something extra at the end of this. So with that, let's kick off and see what I've got on some slides here. So first off, we want to look at advancements, and really to look at advancements, we really need to know a little bit about the past, where we came from with PID. So a very quick jump back in history, and we can jump all the way back to 1962. Many of you will have read Silent Spring by Rachel Carson. Back in that era, people were starting, the very start of getting interested in the environment and what man-made efforts are doing to kill off certain areas. So really, I think 1962 is very much the start of people, the communities getting involved. Moving on till 1969, and the United States, the people had really had enough of industrial accidents. And 69 was when the famous river on fire in Ohio. I will not even try and pronounce the name of the river which was on fire. But this was kicking off when people were saying, we've had enough of this. we expect our government to do something about it. And that is where in 1970 we had the start of the EPA being formed in 1970. And that actually came about, if I'm right, that was President Nixon at the time, and he had his one of his famous what the country is going to do. This was the third famous speech he made of what the country was going to do, and this was the start of the EPA. So it took a few years for the EPA to really get their act together after that, but by 1980, they had already got to the point of identifying hotspots, nasty places around the country, and they had already identified over 200 sites that we would later on start to call Superfund sites. And that's around about 1980 when that was really happening. Now, once you've got a government agency, you now have the start of money being able to be spent on some of these environmental projects. Once you have especially government money involved in those projects, you now have something worth instrumentation companies wanting to make a buck and make instruments to help people at these Superfund sites. So I'm going to jump slightly sideways and ask the question, why PID and not some other technology that is already out there? So first off, I'm going to ask, what would a perfect instrument be? So very quickly, I think a perfect instrument would be able to detect and speciate every known gas. It would be accurate to ppm, and sometimes we would need ppb. I would need it to be fast with almost real-time readings, and I would want it to be portable and handheld. I think those are kind of a perfect instrument. So what is perfect? Is a mass spectrometer perfect? Well, I don't think so. I do think it's good. It can deal with detecting and speciating almost everything. It can do the right levels, ppm and ppb. However, a mass spectrometer is definitely not fast in real time. It is also definitely not portable and handheld. So we need to think about some other device. And that is where PID comes into it. Let's have a quick look. Is PID able to detect and speciate every known gas? Well, we can detect them, or most of them, but we cannot speciate. And just want to be very careful on that point. Although we can detect hundreds of different volatile organics, we cannot speciate. Even though our handheld instruments might tell us a reading on the screen, for example, benzene, the instrument would still respond to other volatiles. So a very important thing to point out there. So we are accurate to ppm and sometimes ppb. PID does that great. We are also fast, real time, almost real time, a couple of seconds response time for most handheld PIDs. And PID is also portable / handheld, very small, lightweight. So we could argue we've got 3.5 out of 4 yeses from a PID instrument, which is better than a mass spectrometer. So that is why we are really using PID. It fits most of our wish list. So a little bit of history. Early on, the first instrument that people were using at these Superfund sites was the HNU Model 101, often just called the HNU 101 for people who were ever using instruments back then. It did the job. It was a PID instrument. It was bulky. It had a large analog gauge, so accuracy no better than 7 or 8% in accuracy. It was fixed to 3 very basic ranges. However, it did its job. It was the start of the PID industry. It sold well. It sold very well, actually, for all of those original super fun jobs. It did very well indeed. Moving on from there, around about 1985, I couldn't find a first sales date, but Photovac were the first people to put a digital handheld unit out there. Again, an advancement. It was now handheld, digital, battery powered, so much better than the HNU 101. The first instrument that really looked like a true handheld PID of today. But look at that, that was back in 1985. Moving on from there, the next unit to really give an advancement came from Ray Systems in their Mini Ray 2000 unit, around about 1990. Probably the biggest selling PID of all time. There were whole generations of people who went to school for environmental studies, and they were taught using the Mini Ray 2000 technology. Great. It was a small advancement from the previous units. It now had better data logging. It lasted much longer, backlit screens, some things like that. A great unit. However, up until this point, all handheld PID instruments would have known problems when using with humidity and to do with contamination and humidity especially. And I will talk some more about this later on. But up until this time in the 1990s, we still had no way of getting around a traditional problem of humidity and contamination problems. So moving on in the timeline a little bit, ion science comes into the game. Round about 2000, it was right in 2003, our first entry into the PID market. And we were talking about something called fence electrode technology and how we had a way at Ion Science of dealing with this traditional humidity contamination problem with the use of an extra electrode built into the detector. And again, we will talk a little bit more about that because it is so important with our modern PIDs, how we do that. Timeline-wise, moving on from there, there were advancements. Ray Systems upgraded theirs to the Mini Ray 3000, round about 2010. Again, very small technical changes. The battery had more capacity, the back screen was a bit brighter, but essentially it was the same Ray Systems PID technology. It still had the traditional problems of humidity and interference there. And again, later on, I will talk about one feature. Ray Systems would tell you that they had humidity compensation built into their instrument. And I will talk about that later on. Again, very important. But timeline-wise, then Ion Science with a new, more modern-looking unit comes on the scene with Ion Science Tiger, a miniaturized PID sensor, again, using this new fence electrode technology that deals with the humidity problem. Again, we're getting much newer now. And we get almost current day with a new, slightly sexier looking version of the Ion Science Tiger unit. Again, completely up to date with every bell and whistle that you can have on a PID instrument. Most importantly, with this fence electrode technology built into it. So I think if I can get the buttons to work properly here. So a little bit of a deep dive in some of the PID features and the technology. So first off, let's consider lamps. I think most people will be aware that 10.6 EV or electron volt is the favorite and ships with most PID instruments. However, there are other lamps available in our PID detectors. And you'll see I'm showing here there is a 10.0 EV and an 11.7 EV. You can see here with the blue 10.0 offering, with 10.0 EV being produced by the lamp in the detector, there is enough energy to ionize and detect acetone that has 9.7 electron volt ionization potential. But there is not enough energy to 10.0 is not higher than 10.1. So you cannot ionize and measure isopropanol. If you needed to do isopropanol, you would have to use the 10.6 or higher lamp to be able to do that. Likewise, if you needed to do methanol that has a 10.9 electron volt ionization potential, 10.6 EV will not do it. It is not high enough. So you would have to choose the 11.7 optional lamp. There are, however, some issues, some things we need to know about an 11.7 lamp. They are really difficult to make. That makes them expensive, and they also have a very short shelf life. In comparison to the standard 10.6 lamp, 1 to 3 years easily from one of those lamps. The 11.7, we will at maximum able to get 3 months of life from one of those lamps. So only use an 11.7 lamp when you really have to. The cost and complications mean it is not a good idea to just say, oh, 11.7 is better. It means I can detect everything. Not a good way of thinking about things. So a very quick look there at lamps. Now, along with different lamps, we have different what we call response factors. So over time, chemists and instrumentation manufacturers have looked at hundreds of different volatile organic gases, and they have seen how they respond when you put them to a PID instrument. They have put those on a list and given those what we call a response factor or correction factor number. For example, here I'm showing from the Ion Science website for gasoline, we see the gas response factor on the middle line from the red section of 0.9. That means that when testing gasoline, we found it to be slightly more responsive than the industry standard isobutylene. Therefore, we gave it a number slightly lower than 1 of 0.9. Likewise, if we were to measure a gas that was slightly less responsive than isobutylene, we would give it a number higher than 1. And so that information is available. It's on our website. It's all over various download sites. And we can search for it online if we know the CAS number or if we know the gas name. And we actually have a very large downloadable chart and list, over 800 gases listed, and telling us what the response factor would be for each gas. Now, if a response factor is shown as being 5 or lower, that means it's very nice and able to be used with any of our lamps and still get measurement down to parts per billion level. If a response factor is higher than 5, I would ask us to ask ourselves, would a 5 response factor, which would ask the instrument to multiply all the screen readings by 5, be a problem? So just imagine we had, for example, I think it's the third line down, acetaldehyde is shown with a 5.5 response factor on the third line down. If there were, let's say, 1 ppm of something else, not acetaldehyde, but some other volatile in the air, the instrument would also multiply its response on the screen by 5.5 and give us potential numbers that we don't understand, and we might just call those unneeded interference. So as a rule of thumb, if the number response factor is higher than 5, I would suggest we ask ourselves those questions. Is it right to be using this particular lamp setup right now? So we'll move on just a little bit. So here we get the really, really interesting stuff. So traditional, this is the most interesting bit to try and explain with very careful words to get things right. So traditional PIDs were known to have problems in the field when there was high humidity around. We might say to ourselves, well, it's never high humidity where I am, it's only ever dry, what's the problem? However, if we are making soil samples, we might put a few scoops of soil into a jar or a baggie. We then might warm that sample, and that sample has moisture in it. We warm that moisture and we make artificial humidity in our jar sample, in our bag. So please don't have anyone tell you, oh no, there's never any humidity where I'm working. It's just not true. So the traditional problem, people would start their work in the morning. They would do all the best things they could. They would test their handheld PID using a cylinder of calibration gas. They would do a bump test and get a perfect 100 reading. They would apply 100 ppm of isobutylene, and the instrument would read 100. They would go out into the field that day full of confidence that their instrument was working wonderful, 100% ready to take readings. They would go out into the field, they would start taking their first readings, and they would find numbers ticking up very slowly, slowly but steadily going up, up, up. Just reading 0.1, a few seconds later, 0.2, 0.3, just slowly up and up. The small diagram on screen shows you might press the 0 button, take the reading back to 0. However, slowly but steadily, continually, the numbers would start going back up again. Okay. This is a known problem with PIDs and humidity. And for a long time, the industry was told, oh, too bad, that's what PID does. The only thing you can do is send your instrument in to be serviced. The service company would take apart the detector. They would scrub the electrodes and the lamp inside with methanol and try and get rid of any contamination. And send you the unit back along with a large service bill and tell you it's all good to go. However, you might the next time or the second time or third times afterwards have the same problem again. So this is what I call the primary effect of humidity. It's the one that people are aware of, and it was considered normal for a long time. So I just show this. Hopefully you're seeing this moving on the screen here. With a traditional detector, your VOC and humidity would travel through the detector. As time goes by, a small layer of contamination shown as the brown chunks on the edges of the detector cell attaching to the electrodes, a layer of contamination. This is microscopic. You cannot see it. It is the result of unperfect ionization taking place, and it leaves this microscopic layer. Now, the problem only comes when you have humidity as well. Humidity attaches itself to the brown colored contamination, turning it blue into wet contamination. And the problem we know with things that are wet, let's remember why we don't use a toaster in the bathtub, that the water and electricity don't mix. And in this case, we have conduction taking place. The red mark there in the middle is showing we have conduction able to take place between electrodes using the path of the wet contamination. And that is what shows on screen as the readings going up, up, up. So this was a traditional problem. At Ion Science, we remember that contamination. We call it conductive residue after photoionization. If we shorten that, we have CRAP. So we have our crap problem with our conductive residue. Traditional problem. Now, at Ion Science, we looked at this problem. We said, how can we deal with that? We have a different design. So a modern design has the main gas path follow, not actually going through the sensor. Only a small amount chooses by diffusion to make its way through a permeable filter. It makes its way into the detector. Right now, the graphic shows still having conductive residue. We can't stop that. We show the detector wanting to show current flowing along the conductive path between positive and negative electrodes. However, on the next slide, if I can make it do the right thing, here we go. Ion Science has added an extra electrode. That electrode is embedded into the walls of the detector. So now, as the current tries to flow through the conductive crap layer, now it is broken its path, and the middle electrode takes that signal away to ground. We have completely taken away the traditional problem with signals slowly ticking up, up, up. So essentially dealt with that problem. Humidity and PID, the traditional problem dealt with. Wonderful, we say. Let's move on a tiny bit. However, I would like to introduce to you the secondary effect of humidity. Now, we never normally get to see this effect because we test our PID diligently with calibration gas, and calibration gas is completely dry. Okay, no moisture in the isobutylene and air mixture in our calibration gas. However, real world readings don't come with completely dry background air. They come with all mixtures of humidity going on. Now, the problem is that as we get higher humidity mixed in with our VOCs, that humidity will actually absorb the energy being produced by the lamp in the detector, and it actually stops some of the energy ever reaching the electrodes and the intended gas it wants to ionize. So we just lose signal before we even get to make a signal. This effect is so repeatable and in fact highly repeatable. So long as we know the temperature and the humidity, this drop in signal will be the same percentage every single time for a particular manufacturer of instrument. And the graphic is trying to make us think of that as the energy headlights are fog lights. You have fog around, the fog will just absorb the light from our car headlights before it even has a chance to light up the road properly. That's our secondary effect going on there. So, an example of what we have going on, a perfect reading, I'll use 100 ppm again for this secondary effect. Now, I can tell you that the decrease in reading, all PIDs have a decrease in reading. It varies by manufacturer. And we know that it matters how big the detector is physically, how much space there is between the lamp and the electrodes. That is what is actually changing the readings. So a bigger, more old-fashioned PID will have worse readings, worse response. It will show lower readings. And a new modern, smaller micro detector will do better, will show less of a drop in reading. And Beer's law, I love Beer's law, I love my beer. So Beer's law tells us that the drop in signal is entirely dependent on the distance of or how much humidity there would be. That's our B figure. So the bigger the distance of B, effectively, the bigger a detector physically, and the light from the lamp literally is being absorbed before it makes its way to the detector. Again, Beer's law, very easy to remember that one. So very easy actually to do our own tests. Many of us will have cylinders of calibration gas available. Many of us will be used to doing a bump test. Now, the picture is showing a bubbler. Some lab equipment, some lab folks will be used to this. We have water in the bottom of the bubbler. On the right-hand side is a blown-up version. There is a small air stone or frit, they're sometimes called. We push isobutylene gas, 100 ppm, through the water. The gas will pick up as much humidity as it possibly can based on the temperature and, in fact, the air pressure, I guess, in the room right now. But it will absorb what it can to get to close to 100% humidity. We can then connect our instrument to that and see how it reads. And here, I took a freshly calibrated instrument that was reading 100 ppm moments before, and here it is now through a bubbler with 100% humidity, we see a drop in reading. So actually something that is not too difficult to do. You may say, oh, well, Justin, I don't want to spend hundreds of dollars on a bubbler to go and test this myself. Well, let me see. You can do a cheap version yourself. right? Go to the store, sacrifice the life of a inexpensive water bottle. You don't even need the air stone at the bottom. It does work just fine like this. Here we see. I ended up with a reading very similar. So I'm getting, what am I getting there? 3 and a bit percent. Sorry, no, 7 and a bit percent drop in reading with my very simple test. So I would encourage anyone, if you're inquisitive, maybe go and do the same test for your own PID you're using. And I will tell you from my own experimentation, Ion Science will always drop the same readings, and a couple of other brands, when I go and test them, will have much higher drop in readings. So the question really is, let me see. Now I know there is this secondary effect due to humidity. Which would I rather use? An instrument that drops lots of signal or one that drops less? So the important thing is knowing about it. If you don't know that there's any secondary effect due to humidity, you might think your readings are perfect, but now you can do some tests. You can take that into account. So let me see, moving on a little bit. So again, I hear you say, but Justin, a couple of manufacturers out there are talking about humidity compensation. They claim humidity compensation in their handheld PIDs. Well, what really is that? So, this graph is taken straight from one of those other manufacturers. They show you with humidity compensation turned off, they expect to get readings dropping about 50%, showing so at 100% humidity, dropping readings by 50 ppm. And they tell you themselves that if you turn humidity compensation on, it won't be perfect, but you might get back to somewhere around 10, 15% drop in signal. So are those claims true? Well, I'm inquisitive, so I go and test it myself. I was expecting to see a drop in signal when I tested one of these instruments claiming humidity compensation. But it overshot and every time was reading 114 or 115. So for me, that just tells me it's important to know about this secondary effect. Consider doing the test yourself on whichever instrument you are using so that you can take it into account. Now, so we'll move on from there a tiny bit. Yeah, so really, from that secondary effect of humidity, I hope you're filled a little bit more with some information. You could have a reading as low as 40 or 50% drop, and you could have an instrument overshoot. The best way would be to think about taking some readings, sacrifice the life of a water bottle. Consider doing that test yourself, okay? Information is power. We can then deal with it, choose a different instrument, or maybe make a correction for those readings in our data. Okay, let's move on a bit here. Somehow the forward button is always a problem when you're sharing a screen. Let's go again. So, just moving on from there very quickly. At Ion Science, very quick, shameless plug, we then put that same PID that we know doesn't have the traditional problems. We build that PID into wearable, handheld, and also a whole range of fixed wall mounted detectors. And it's that that's that sensor, the prowess with the sensor, that means ion science can call itself, we arguably say, the best PID sensor in the world, and we are definitely making more PIDs nowadays than anybody else. Shameless plug out the way. I think we're about at the point where we can ask for any questions. I do think I was going on just a little bit too quick with stuff there, but I'm sorry about that. I get just so enthusiastic about trying to share some of this interesting stuff about PID sensors. So if anyone has got questions based on that, I'm very happy to try and answer.
So we can utilize both the question and answer, as well as, like Scott Swanson indicated, if you have a question that you'd rather talk through, you can raise your hand, so to speak, and we can manually unmute you. So just to give a little bit more context of kind of what we're going down the road with is directly related to what Justin was sharing, is these environmental conditions that result in less than ideal readings. And so if we're working in challenging environments where we have either a significant amount of humidity or where we are trying to apply some of these correction factors for specific gases, it just like any instrument, this PID technology is only as good as the user who's using it and understands the limitations of that technology. And so if we aren't really familiar with those limitations and applying good best practices to mitigate those things, the number you're getting at the end of the day might not be as useful as it could be. And that's really the premise of the PID series here, is to try to equip stakeholders with the knowledge, like Justin has shared with us today, of the limitations and applications of the technology, and then really push that best management practice of how we utilize this technology so that we can make better decisions when it comes to real-time remediation and delineation resource allocation. And so we do have one question that came into the chat. So for oil field cleanup, so hydrocarbons, is there ever a situation where you'd want a FID over a PID? I'll let Justin jump in on the flame one.
So we saw that PID is limited by 11.7 electron volt at its highest end. Anything with an ionization higher, sorry, PID just doesn't have the power to break the bonds to get that measurement. So yes, there can be times when FID is needed. So just thinking about that, what have we got that out there that is too high for that? So off the top of my head, what have we got? We've got CH4, I believe, is too high to do with PID. I believe so. We would have to use an FID to do that instead. The normal rule of thumb, again, from a PID expert, I'm not as expert in FID, but normally you can't do quite as lower numbers. So you can't really get to the parts per billion level of things with an FID. The other thing is an FID will completely break apart your sample forever. It is burning it to get a reading. PID does not do that. The PID sample will instantly reform back to its original gas. If you wanted to, you could collect that in a bag and send that sample off to the lab. With an FID, you'd have to be making fresh samples and send that off to the lab. Hopefully that answers that one enough.
Yeah, so we had one come in with the question and answer. So the question is, would a carbon filter added to the detector address some of the moisture and humidity issues?
Okay, we got some smart cookies here who have thought about this before, I think. So, um, when Ion Science has looked at this problem in our own labs, we have looked at, can you put various filters on to start with? Can you put an absorbent filter just to try and get the moisture before? The problem was, especially at low levels, any filter you use to try and take out the humidity before it gets to the PID sensor was also taking out minute amounts of other things as well. And we could never completely control what other things. So the purist says it is best to do things with as few filters, things like that in line as possible. Okay.
Awesome. Thanks you, Justin. So we got another one. What steps can a field staff take to reduce risk of humidity entering the PID? So can PID operators service the instrument to rectify humidity damage, or must they always be serviced by the manufacturer?
Okay. A traditional style PID, um, it's very difficult for a user to service those units themselves. They were made to be taken apart on a technician's bench, cleaned and dried bit by bit. Not something you would want to be doing, for example, in the truck, in the cab of your truck, right? However, servicing of newer modern style PIDs has become much easier. They are split into a lamp and electrode stack, which is almost disposable nowadays. I'm sorry, I don't have a slide showing this. I was remiss in that, sorry. But they've become very simple as they've become miniaturized and smaller. The user could now do a simple cleaning, even in the environment of, let's say, the cab of a truck. You would clean the lamp using alumina oxide, a very fine abrasive powder. You would probably fit a new electrode stack. The component is maybe $60, something like that. Fit that back in the instrument, do a user calibration, and you are good to go. Very, very simple. Again, these newer generation detectors much better at dealing with that. Hopefully that answers that one okay.
Yep, awesome. Thank you, Justin. So we, through collaboration with stakeholders and working with our Reclamation Advisory Group, have had a couple questions pop up that really got this whole discussion around PID workshop started. And that is, for many of the practitioners, what we're looking at utilizing the PID for is delineation of hydrocarbons within soil matrices. And so the general practice for utilizing the PID for detecting contamination within soil is the headspace development techniques. And a lot of the times that takes the form of using a Ziploc bag. So the standard practice is to grab a grab sample of soil, throw that into a Ziploc bag, close that Ziploc bag, homogenize the soil a little bit and giving it time to come to equilibrium. And what you're really doing is you're allowing any volatile organic compounds to actually volatilize out of that soil sample. Because we're in North Dakota and half of the year we're in frigid or freezing temperatures, a lot of times those Ziploc bags get thrown on the dashboard defroster so that you can expedite that volatility of the contaminants and hopefully have a better reading. But along those lines, there are a lot of opportunities for there to be user variability. And so when we're talking about grab sample, how we're grabbing that, whether it's literally with our hands or a continued use shovel with cross-contamination, or if we're using more strict protocols around like soil plugs that are disposable, And then also just like size and volume of samples relative to headspace development, as well as this definitely humidity management concern. And so that's a really loaded question, but I'd love to hear your approach in when you're interacting with industry field specialists on some of those best practices that you integrate in specifically that headspace development reading.
So it is a big question all around, and you're right. When you are so so the EPA has in the past done a wonderful job in saying what you do when you have a pure air sample. They're much better at that rather than giving definite instructions, implicit instructions of what to do when you are wanting to deal with more water style systems. I can tell you that people get very, very smart, ingenious solutions. I've seen people with water waste treatment build their own floating style detectors with a tube going higher up, so they can get literal headspace in water treatment works. So long as we make sure we keep only only air going into a PID instrument, we are good. The moment we put actual water into it, problems. 100% humidity, no problem. The instrument deals with it. But water, no, that's when you will kill a PID instrument pretty quick. But apart from that, all goes, all goes. I would suggest from many discussions that directly putting baggy samples on the dash of a truck, not such a good idea. It's actually better to put that sample under your armpit inside your jacket for a few minutes is a better way to more evenly heat as much as needed. Just the heat from the blower on the dash sometimes just a little bit too vicious, if that makes sense. Okay. But I don't have too much more on the day to day of how to do that. My suggestion always, though, is nobody's asked the most difficult question. How often should I calibrate my instrument? I'm waiting for someone to type that quickly, but no, I'll answer it now. So, the most difficult question. So, calibrate an instrument as often as you need to be confident in the results it is giving. If you need super accurate to within 1 or 2% readings, well, please calibrate and bump test at the beginning of the day and the end of the day. Statistics tell us, therefore, any readings you take in between have to be pretty good. So calibrate more and often as you can. If you can't do it that often, okay, but whenever you can, more and often is definitely the way to go with any PID bump test and cal.
Yeah, so lots of room for improvement is kind of the theme around the specific challenges that we have in the environments that we're trying to do delineation of hydrocarbons, specifically that soil contamination potential. And so we have a research proposal and developing research methods specifically looking at what are the most significant factors in contributing to variability from user to user or sample to sample within these soil matrices, trying to refine best management practices. And so what that ultimately is looking for is, can we standardize sample mass or volume, headspace volume, that ratio from contaminated material to headspace development volume, and then also temperature of the sample, so that we're not I mean, actually, the under the armpit's pretty interesting because we all do run the same temperature, whereas the defroster on the front of your truck might
Yes.
variable quite a bit more. We are looking at opportunities like utilizing some of the lunchbox heaters that have come out into the marketplace, where
Okay.
you want to have a nice warm piece of leftover pizza at lunch, and some of these other opportunities to kind of rudimentarily get to just a more consistent
Yes.
environment for taking readings.
So the old school jam jar was definitely a better technique. You actually had a known volume. You could very consistently put 2 or 3 teaspoons of sample in a jam jar, seal it up, and warm it much better than you can with a Ziploc bag.
Yep.
The amount of headspace is so variable depending on the size of bag, exactly how you choose to seal it before warming the sample. So yes, I can't see the industry wanting to change away from that, but any way of um, taking the uncertainty out of that would be great. Yeah,
Yep. So that's where we are ultimately going, is that we're not suggesting that suddenly we need to go back to a VOC jar with a trap and or what's the two-way valve called? Trap and purge type valves for
yeah,
doing readings on a closed cylinder like a jar. But if we can kind of standardize that process for at least the clean wall reading, so not the 500 readings that it takes you to get to that clean wall, but that one reading at the end where you're feeling like you're finally getting to that limit or that delineation of the impacts. It would be application of these best practices in there that our research questions are mainly focused around. And we are suggesting that we use a purge and trap type VOC vial for those types of more refined practices for utilizing the PID for hydrocarbon contamination. I got two other questions for you, Justin, that have popped up. The other one that we are working with is because we're in the elements of North Dakota with our oil and gas development, there tends to be instances where we have accumulation of stormwater on pad, and regulations de tend to dictate that you have to confirm there is not contamination of that rainwater or stormwater from hydrocarbons before it can be dewatered off the pad. There are methods that are being utilized by practitioners that utilize basically wet chemistry and colorimetric changes based on solvents on the tailgate. I'm not a huge fan of doing wet chemistry in the field, and so I am interested in this percolator or the glass system that you were talking about for being able to basically volatilize materials that are otherwise dissolved or emulsified within a water sample, and how that system is designed and utilized for maybe getting at that answer of, can we in real time utilize this technology for delineation of hydrocarbon contaminated water?
okay. So from the practical side of things, Um, if you have what you believe could be contaminated water, to put that into a clean jar with knowing you have plenty of headspace to shake that up is going to do a pretty good job of giving that volatile a chance to make it to the air section. And if you can warm it very slightly, even better. So I think practically, yes, that is probably the way to go. Um, the bubbler setup you saw, um, I think probably too many chances of getting lab equipment messed up and dirty and needed cleaning for a tailgate system. Um, but what that system does, as best as we can, it very quickly allows the gas to pick up um, any of the volatile there is. So yeah, that might be worth looking at that a little more. Maybe with the special disposable water bottle system, that you could a simple test and throw that away afterwards. I think that would be fun exploring.
Those
Yeah.
are the type of solutions that we like, off the counter
Right.
at the gas station opportunities to advance advance the use of the tools that we already have.
Yes. Of course, the best tool we have is our minds and information. That's worth anything more than we can buy and put in front of us. So yeah, some smart thinking, just remembering. I think those some of those key things we've seen, we can detect hundreds and hundreds of VOCs, not necessarily speciate. We've seen some of the issues with 11.7 lamps, for example. We know there are response factors. We don't want them too high. If we remember all of those things and take those along with us, I think it'll help all of us be more powerful in the field.
I couldn't agree more.
Yeah.
Thank you for that insight. I think this will be an easy one to answer, but the question is, like, well, utilizing PID for field screening soil contaminated with heavier hydrocarbon mixes, say something less volatile like hydraulic oil. Do you have any recommendations on maybe like how to configure the system for those types of less volatile oils, or if that's just one of the limitations that we need to understand are contaminants of interest, and whether or not the technology is appropriately allocated to that?
Well, you're right. So I think we have to remember we are volatile organics is what we can do when something stops being organic or sorry, volatile is it makes it so much more difficult. Again, you mentioned cold conditions. I'm normally based in Vermont. Equally, we have those chilly winters. I remember gas station across the street from me, gas spill. I think there were 40 gallons all over the floor. And I got a phone call from the local fire department. How do we deal with all of this? And I think we were negative 15 Fahrenheit that day, something like that. And I just said, get a shovel,
Hmm.
shovel it up with the snow. It's like, it's not going to do anything. It's not going to be volatile in any way. Again, um, with those heavier things, unfortunately, yeah, we can't really do too much apart from consider warming is the only way we're going to make them volatile enough to measure nicely.
Yep. Awesome. Great answer. This one is actually, thank you, Dr. DeSutter, for prompting some of these good discussion points, because this one I also don't know the answer to. And I think it comes back to some of the newer designs of like the pump and the space within the ion chamber. And that is like, how small of a headspace can one hold before like a vacuum impedes the instrument's ability to make a good reading. So like if we're using a capped glass jar, any insight on like when we would need to implement a trap and purge type two-way valve, whereas like what is that limitation of, okay, we can still get a reading even though we are technically kind of putting a vacuum on the system.
Yes. So I think we need to look a tiny bit about flow rates of the instrument. Um, most of the instruments are somewhere between 250 and 500 milliliters per minute as the flow rate through the units. Um, if we look at a standard jar, having a look at those, I'm guessing those are they're probably going to be somewhere half a liter ish or a tiny bit more. So yeah, we'd have um, we'd have there 1 or 2 minutes worth of sample of being good. No system is truly leak tight. I suppose it's going to try and make up some air at the same time. So um, yeah, it's always difficult. You will end up getting reduced readings at the end because it's being made up and diluted.
So is
Um,
there a trigger point on those on your instruments for when that if that vacuum it reaches a certain negative
on
pressure that it will shut down?
Yeah, on our units, when the unit sees a flow go below 100 milliliters per minute, it will activate its own alarm and shut things off.
Yep.
Um, So yeah, it's interesting. Um, Again, our unit has a feature you can have it take a 10-second average sample. You would just press the button, go. It will 10 seconds worth and average that. Some people like that for this headspace. Again, do you take the highest reading? Do you take the reading after 20 seconds? How you do it? That takes the question out of their hands a little bit. If their procedure says take an average 10-second reading, record what's on the screen.
Yep.
So,
Yeah, Dr. DeSutter's putting out some of our thermodynamics and PChem approaches of, well, if we can heat that bottle up, PV equals nRT would suggest that we might even have a little extra volume to pull out.
okay, yeah.
That is the queue of questions that I am seeing. And so I'll give folks just a little bit more time to throw in anything that is burning. Otherwise, there will be a survey that I send out later today with a little review of what we talked about today and its applicability to the participants, as well as suggestions for future topics. And so if we really want to dive into calibration specifically, or if we want to look at headspace development best practices, so how do we take a sample, those types of things are all on the table. We anticipate being able to host webinars and even have in-person workshops associated with this PID series going forward, targeting that 2 to 3 workshops a year. And so we really feel like there is value to continue having these discussions, and we want to continue utilizing the resources out there, like folks like Justin Blackman, who have a wealth of knowledge on the application of these technologies and the limitations that they pose, and having that guide our practices within the field of remediation and reclamation. And so with that, I'm going to bring us to a close. I want to thank everyone for registering and participating today, especially thanks to Justin Blackman for his willingness to come and share his insight on the topic. And then just ask folks to keep an eye on their email for that follow-up survey so that we can better serve all of you stakeholders. So thank you guys so much, and I hope you have a good afternoon. And for Justin across the pond, have a good evening.
Thank you, everyone. Bye bye.